We'll take a look at a real-world example of using variation of parameters, and this one will involve the flow between two compartments, in this case lakes. We've tackled problems like this before. The only thing is our lakes have typically fed into one another in a complete loop. And so that's what enabled us to use our techniques for solving systems to solve such a problem. But this one will be a little bit different because it will have a non-homogeneous term. So let's take a look. Consider two small lakes, Lake 1 and Lake 2. Suppose that mercury runoff makes its way into Lake 1 at a concentration of 2 milligrams per gallon on the initial day. However, the concentration decreases by 0.1 milligrams per gallon each additional day. So notice that our concentration is changing. The mercury water flows into Lake 1 at a rate of 100 gallons per day. From Lake 1, the contaminated water flows into Lake 2 at a rate of 100 gallons per day. Water flows out of Lake 2 at a rate of 100 gallons per day and runs off into the ocean. So we're going to construct a model, assume both lakes are initially clean, and contain 5,000 and 10,000 gallons of water, respectively. We'll solve and describe what's happening in the long run. So as we begin, we need to think about what are we going to be modeling over time. And it probably makes the most sense to model the amount of mercury. And so I'll just use X and Y to describe these. So let X represent the amount of mercury in Lake 1 after T days. That right away, and this is going to be measured in milligrams. This is going to give us our units of our differential equation, which will be in milligrams per day for X. For Y, we'll do the same thing. It's just going to be for Lake 2 after T days. So we want our units to be in milligrams per day. It's something to keep in mind as we construct our model here. So here we have a lake, we have another lake. We have mercury coming in, and then the contents of Lake 2 coming out, Lake 1 going out into Lake 2, and then Lake 2 just dumps off into the ocean. So when we think about this unit of what's coming in as far as the concentration of mercury, we should note that this is just on the initial day that we have 2 milligrams per gallon. So let's look at the milligrams per gallon as a function of time. We know that on day 0, the concentration will be 2, but 1 day later it'll be 1.9. 2 days later, 1.8, and so on. And so it would make sense to say that we start off with 2, but we decrease that by 0.1 milligrams per gallon per day multiplied by the number of days. So we can see after 2 days, we'll subtract off 2 increments of 0.1. And this is the number of milligrams per 1 gallon coming in. Of course, in order to get milligrams per day, we need to cancel out the gallons. And we can do that because we know 100 gallons per 1 day are coming in. And that introduces days and cancels out the gallons. Inside of Lake 1, we know that this is initially clean, so I can go ahead and write this as x of 0 equals 0. And then what flows out of here, again, I have to think in terms of milligrams per gallon. Well, we know that inside of that lake there are 5,000 gallons, and how many milligrams are inside of here at any given time? Well, that's exactly what x describes. That's going to be a variable amount. So there are X milligrams distributed into the 5,000 gallons because we assume it's always well mixed. And then we have 100 gallons per 1 day coming out. Similarly here, this will just be Y milligrams per 10,000 gallons multiplied by 100 gallons per day. Now we can collect the appropriate terms and write our models. I guess we should have also said that y of 0 equals 0. And now we can write dx dt. So it's going to be rate of milligrams per day in. Well, that's going to be just the 2 minus 0.1 t times 100 which I'll go ahead and write as 200 minus 10t. And that will just make it so that I distribute the 100 into this expression here. And then I have minus the outflow. So this is the inflow, right? And even though it has a minus sign, keep in mind that it's just decreasing every day. Then what do I have? Well, I have the 100x over 5,000, which I can cancel out a couple of zeros here and make this x over 50. Furthermore, it might just be easier to write, you know, whatever 100 divided by 5,000 is, which is 0.02. So we can write minus 0.02x. We get a double whammy here. We actually get the outflow of lake 1 being the inflow into lake 2. So that's going to be a positive 0.02x minus the outflow, which will be 100 over 10,000. And that should give us 0.01. So we have minus 0.01y. And we have our initial conditions here. So we see that there's this term right here, and this term has not been allowed when we solve first order systems and computing eigenvalues and eigenvectors. This term is actually what causes this whole system to be non-homogeneous. So notice that we don't have the lakes flowing back into one another. We certainly could, but things could certainly get more complex. So I need to write this in the form where I have my two derivatives inside of a vector. So that's my dy dt vector. The quantity that we're calling p of t is going to be the coefficients of x and y. So this is our p of t matrix, and then this is what we call our capital Y matrix. This is just going to have the coefficients of x and y in the top row, coefficients of x and y in the bottom row. We have a negative 0.02 times x, and then we have 0 y's in this first equation, so let's put a 0 there. For the second equation, we have a positive 0.02 and a negative 0.01. And then we have, in this variation of parameters method, we could have this non-homogeneous vector g of t. In our case, for the x of t equation, this will be 200 minus 0.1t. The second equation doesn't have any non-homogeneous terms, so we could just write a 0 in there. The solution process, in order to solve this, we need to solve for y sub p, and the way we do that is by solving the homogeneous reduction of this system, much like we've encountered before, which would be p of t times y. Now we know how to do that because that's just going to amount to having this matrix here, finding its eigenvalues and eigenvectors, and then constructing the solution like we have in the past. So let's go ahead and find the eigenvalues and the eigenvectors. Now, here are the eigenvalues and eigenvectors that we get. Notice that they're both real. This corresponds to the fact that both of them are negative, means our equilibrium point that we're dealing with will be a sink if the system has any, but it would be a sink. And our solution, y sub p, would be k1 e to the lambda 1t times v1 plus k2 e to the lambda 2t times v2. So for us, that would mean that our x, I'm sorry, not yp. I wrote yp, but I should have been writing yh. My apologies there. So yh. And this will be the x of t and the y of t that we get plugging in our lambdas. We'll get, in the top, we'll get k1 e to the negative 0.02t times negative 0.5. And then in the bottom row, we'll get k1 e to the negative 0.02t times 1. That's for v1. Second term will be k2 e to the negative 0.01t times v2, which in this case will have that term eliminated. k2 e to the negative 0.01t times 1, which is that second component there. All right, that's what that amounts to. Now we need to use our method in order to find the particular solution. And remember, we need to get this x of t matrix, which we, in fact, already can construct. That's going to contain our two solutions, x1 of t, y1 of t, x2 of t, y2 of t. All right, so there's x1, there's y1, there's x2, there is y2. So solving for y particular now, and once we get that, we'll be able to just sum the solutions. Now we do actually have to solve the original dy dt equation, but we know that we need this x of t matrix, and that's just going to be basically our two solutions, right? And we don't need the arbitrary constants there, so we actually just want the solution vectors, which would be negative 0.5 e to the negative 0.02 t and 1 e to the negative 0.02 t. For the second one, we'll have a 0 e to the, so this will just be a 0, and this down here will be e to the negative 0.01 t. So x1, y1, x2, y2, barring those arbitrary constants. So we are finding a particular solution. Okay, so now what do we need to do? Well, now we need to we need to find x inverse, because our solution is going to boil down to yp equals x of t times the integral of x inverse of t times g of t dt. All right, now let's compute our Wronskian, which we're going to need, and our Wronskian is going to be part of x inverse. So let's compute what w of x would be, and that is, recall, it's going to be x1 times y2 minus y1 times x2. So here we have x1 and y1 and x2 and y2. This is equal to x1 times y2 minus y1 times x2, otherwise known as the determinant. So it's the product of these two along the diagonal minus the product of these two. So fortunately, this is going to zero out. So the second term is going to be 0, y1 times x2. But when we multiply these two together, negative 0.5 e to the negative 0.02 t times e to the negative 0.01 t minus 0. We actually combine these into 1 and make this negative 0.5. Common bases, so we can add the powers, will give us negative 0.03 t. To get the next piece of the puzzle, which is this x inverse matrix, I'll go ahead and omit all of the of t's in there, because we don't necessarily need that, and maybe it just convolutes things a little bit. We'll have 1 over the Wronskian multiplied by the matrix containing y2 and x1 switched, and then the y1 negated and the x2 negated like that. All right, let's go ahead and plug things in. So we have 1 over negative 0.5 e to the negative 0.03 t multiplied by y2, so e to the negative 0.01 t will go here, x1 will go down here, and then it will just negate e to the negative 0.02 t. This is still a 0, so we don't need to write negative 0. That will work. And so now we just need to simplify this a little bit. And so you can choose to write this as 1 over negative 1/2 multiplied by e to the positive 0.03 t. Right? We bring that into the numerator and switch the sign. But don't take the negative 0.5 with it, because that's not being raised to the negative power. So this will actually be negative 2 e to the positive 0.03 t. That just makes it a little bit easier to distribute. That way we can just add the powers. So this times this right here will give us negative 2 e to the positive 0.02 t, because we'll have negative 0.01 t plus 0.03 t. And then it'll distribute into the 0, leaving that unchanged. Multiplied by this, we have a negative 1 times a negative 2. negative 0.02t plus 0.03t would give us positive 0.01t. And then when we distribute that here, we'll have negative 2 times negative 1/2 will give us positive 1. Again, we'll just add the powers 0.01t, just like that. So there's our x inverse matrix. Finally, we're ready to write y particular. It's a little bit of a process, but it all comes together. And now we need to write yp, which will be found by taking our x matrix, multiplying that by the integral of x inverse multiplied by g of t, our matrix, integrated with respect to t. Let's plug things in. X is this guy here, negative 0.05 or negative 0.5 e to the negative 0.02t, 0, e to the negative 0.02t, and e to the negative 0.01t. That's just the x matrix. Multiply that by the integral of x inverse, which is this negative 2 e to the 0.02t, 0, 2e to the 0.01t, e to the 0.01t, multiplied by the g of t vector. Now remember, the top part was 200 minus 10t, and the bottom part was 0. And that gets integrated with respect to t. So we copy this down, and let's multiply this out. So when we multiply this out, it'll be 200 minus 10t times this first column, plus 0 times this second column. And therefore, we can really just ignore that second column and just focus on multiplying these two together. So we will have this carried down times the integral of negative 2 times 200 minus 10t multiplied by e to the 0.02t. That'll be the top component. And then we'll have 2 times 200 minus 10t multiplied by e to the positive 0.01t. All integrated with respect to t. All right, almost there. Now we need to integrate each of these functions, and an integral calculator will be invaluable here because this will require some integration by parts. So let's go ahead and produce what that result comes out to. Again, this will just get carried down, and we'll get a vector out of this. Don't forget that we do not need plus c because this is just a particular solution. So here's one way we could express those integrals. And now we need to just multiply, to wrap this up, we need to multiply this matrix times this vector. And remember that the top component here is going to multiply this first column. Bottom component in our vector is going to multiply this second column right here. And then we add the results together. So let's go ahead and carry that out. So if I multiply 1000 e to the 0.02t times t minus 70 times this first component of this column right here, 1000 times negative 0.5 will give us negative 500. Will give us negative 500. And then when I multiply e to the 0.02t times e to the positive 0.02t, these cancel out and just give me a 1. But then I still have that t minus 70 on the end. Now I'm going to add that to 2000 e to the 0.01t times t minus 120 times 0, which is just 0. But now I have to do 1000 e to the 0.02t times e to the negative 0.02t here. And that also is just going to cancel out the 0.02t's and leave us with 1000 times t minus 70. That, remember, this is all a vector. This is all part of yp. So now I need to add this second the 2000 e to the 0.01t times this guy here, the e to the 0.01t and the negative 0.01t will cancel. And we'll just be left with the 2000 times the t minus 120. This actually should be a negative. I've lost the negative sign somehow. So this should be negative 2000. And so that means we'll have minus 2000 times t minus 120. And I think I'll just go ahead and distribute and combine like terms. So in the top, this will give me negative 500t plus 35,000. And in the bottom, we'll have 1000t minus 2000t when we distribute. It'll give us negative 1000t. And then when we distribute here, this will give us 70,000 plus 240,000 will give us plus 310,000. Oh, I'm sorry. No, I take that back because here we're going to have a negative. Here we're going to have a positive. So we should get 170,000 in the opposite direction. Let's double check that. We'll get 70,000. Yeah, so that looks good. Okay, so that gives us our y particular, and we are done with this phase. Now we just need to put the solutions together. So y is equal to yh plus yp. And so we'd have to come back up here. We probably already forgot about yh, but for the first expression x of t, it's going to be negative 0.5k1, negative 0.5k1 e to the negative 0.02t. Y of t, the y homogeneous, is k1 e to the negative 0.02t plus k2 e to the negative 0.01t. Now I have to add on the y particular, and the y particular for the first, for the x of t will be the negative 500t plus 35,000, and for the second that will be negative 1,000t plus 170,000. And so now we need to plug in our initial conditions. Okay, so we know that both x and y are 0 at time 0. The first term will be negative 0.5k1 when we plug in 0 for t. This term will go away. We'll just be left with the 35,000. And then for the second one, we'll have k1 plus k2 plus 170,000. And when we solve this system, we'll get k1 is equal to, let's see, 70,000. And k2 will equal 240,000. So you can see, hopefully, that non-homogeneous things, especially when we get into systems, can get far more involved. If we backtrack, and we're not even doing all this integration and solving by hand, there's quite a few steps to get to it. Again, everything comes in pieces, so it's just important to take our time as we construct these. Let's go ahead and take a look at the graph of this and talk about what happens in the long run. There should be a negative 240,000, but let's go ahead and look at the solution. So all I've done is I plugged in k1 and k2, and we can see that k1 and k2 are plugged in. I have called these equations capital X of little x and capital Y of little x. That way I just remember lake 1 and lake 2. Now here's the graph. Of course, we need to zoom out a bit because we're not really sure what we're seeing here. So we can kind of see that the red curve, that x of t, goes up and then seems to fall back down at around time 36. Let's investigate that a little bit further. So I'm going to come up here and set my y-axis. I like to go in increments and multiples of 10. So I'll go 0 to 10. Nope, still don't see it. Go to 100, go to 1,000, go to 10,000. Now I can see both graphs. And moreover, I can actually see that it looks like the amount of mercury increases and maxes out after about 16.8 days. And the total amount, the maximum amount that Lake 1 will have of the mercury is about 1,588 milligrams. After that, the amount of mercury seems to drop down and approach zero. And that should make sense because from our model, recall that the first day we had 2 milligrams per gallon, but the concentration is decreasing each day. And if you think about it, 200 milligrams, I'll write this out here, so I'll write days until no mercury concentration coming in. Well, let's think about it this way. We know that after that our model is 20 minus 0.1x, or I'm sorry, 2 minus 0.1x. And if you think about that function itself, that's the purple one. The purple one actually reaches 0 after when x becomes 20, right? So at time 20, the amount of mercury, the concentration coming in, actually becomes 0, right? So here you can do this. You can say 2 divided by 0.1, and it tells you after 20 days. So what this means is that it does not make sense to consider our model beyond day 20 because the mercury has decayed down to a concentration of 0, and after day 20, that 2 minus 0.1x becomes negative, and so it makes it seem as though there's a negative amount of mercury coming in, which is what actually causes our graphs to eventually become negative. Now there's always going to be a little bit of a lag, right? Because even though after 20 days the concentration is 0, let me go ahead and change this domain to set our x-axis to go from 0 to 20. Nothing beyond that we want to consider, right? At day 20, when the mercury concentration becomes 0, what we would actually need to do to figure out what happens after that, well, we can probably imagine that if there's just pure water coming into Lake 1 after day 20, then we would just expect that water to continue to filter, because then at this point, the amount of concentration coming in should be defaulted back to 0 milligrams per gallon for days greater than 20. And at that point, we would need to resolve the model, but the model would be much simpler. It would just reduce to negative 0.02x for dx dt, and then 0.02x minus 0.01y for dy dt. And we could solve that system, which would give us this general solution right here. And then at that point, we need to solve for K1 and K2 using the x and y conditions at time 20. So if we take a look at x of 20 and y of 20, there would be 1,538.8 milligrams of mercury in Lake 1 at day 20, and 427.02 milligrams in Lake 2 at day 20. If we use those as new initial conditions, we can continue, to model this beyond day 20. But because of that negative term, nothing really makes sense after 20 days. So it's kind of interesting to see this happen, and of course a much more complicated scenario because you do have the lakes feeding into each other and you have also a changing concentration. So very long problem, but worth the effort, I hope.